Hey everyone, welcome back, and today let's solve Leetcode problem 2466 titled Count Ways to Build Good Strings. So we're given the integers 0, 1, low, and high, and we can construct a string by starting with an empty string and then at each step perform either of the following. So in other words, we have two different choices or decisions to make at each step or iteration. So we can either append the character string 0 0 times, where 0 is actually a given parameter to us, as you can see right here, in the form of an integer, or we can append the character string 1 1 times, or one number of times, and that 1 is also given as a second input parameter as well. And this can be performed any number of times, but the main criteria here is that a good string is a string that's constructed by the above process of zeros or ones, 0 and 1 number of times, having a length between low and high inclusive. And what that inclusive really means is it can be low and high as well. It doesn't have to be strictly in between those two values. And we need to simply return the number of different good strings that can be constructed satisfying these properties, applying these operations between the lengths low and high. But since the answer may be too large, we have to return it modded or modulo by 10 to the 9th power plus 7. I believe it's just a really large prime number used for encryption. So in example 1, we can see that our input low is 3, our input high is also 3, and in this case we have 0 to be 1 and 1 to be 1 as well. So in other words, we can append the string 0 one time in each operation, and we can append the string 1 also one time in each operation. And we want our good strings to be of length 3. So in this case, we have an 8 as an output because one possible valid good string is going to be 0, 1, 1. Right, and that can just be constructed as follows: 0, then a 0, 1, and then a 0, 1, 1. Right, and there are 8 different good strings that have that length of 3, or inclusive between 3 and itself, which actually do meet these following properties. So in example 2, we have our input low to be 2 and our input high to be 3 and 0 to be 1 and 1 to be 2. So what this really means is that we want the length of our good strings to be either 2 or 3 inclusive, and we can append either 1, 0 or 2 1s in each operation. And in this case, we can have 5 number of different good strings that meet those following criteria and have those following properties. In this case, those 5 strings are 0, 0, 1, 1, 0, 0, 0, 1, 1, 0, and 0, 1, 1. Note that they all have a length of either 2 or 3 because that's the range that we're looking for given in these two parameters, low and high. And as you can see, for the constraints, we are guaranteed that high is going to be greater than or equal to low, which is a good kind of base case to guarantee and be sure of. And we're also given that they will not exceed 10 to the 5th power. And we're also given that 0 and 1 are both going to be greater than or equal to 1, but they aren't going to exceed low, so we can actually still make a valid operation without actually breaking the problem's rules, at least once. So with these constraints, problem statement, and examples out of the way, I will give you guys a few seconds to kind of just go over this problem in your head and think of a valid solution, and then I'll show you guys how I would optimally solve this problem in a few seconds. Okay, so there's actually two different algorithms or methods that you can really use to solve this problem. The first part is recursion, and you guys probably kind of picked up that recursion part when I kind of described that we had two different decisions at each step. We can either append 0, 0 times or 1, 1 times, and we can kind of make a decision tree using these two different possible decisions, but that wouldn't be the most efficient of solutions. In fact, the other kind of algorithm to use to solve this problem is actually going to be dynamic programming. But first of all, what is a good observation we can really make in this problem here to kind of lead us to our solution? Well, one observation that we can make is that the problem, really, we can just reduce it to be finding the number of ways to construct strings of length n using that recurrence relation. right? And for the kind of dynamic programming approach that I just introduced, effectively, to efficiently count the number of valid strings, we're simply going to use an extra DP array, or dynamic programming array, where DP at index I is going to represent the number of ways to construct strings of length I, the number of different good strings of length I that we can construct from our two properties. So let me actually comment that out here for future references here, and let me actually zoom in a little bit more. I think that should be good. So DP at index I is simply going to be the number of good strings, or rather I should say ways to build strings, or rather build good strings of length I, right? And of course, we want that length, or I, to be in between low and high, and we will consider that as we actually populate our DP array. All right, so that's what the dynamic programming portion of this solution is really going to be used for, to actually help us efficiently get the number of different ways in that range where I is in between low and high inclusive, right? And basically, for the base case here, to actually first kind of put a base case in our dynamic programming solution to compute future iterations. Basically, the base case is, initially, there's going to be exactly one way to build a string of length 0. That's literally by just doing nothing. So the base case is first going to be setting DP at index 0 to be 1. That's the base case that we build our future or next operations off of, right? And for the actual transition relation part of this problem, essentially for every single length or index I in that dynamic programming array, we can either add a 0 times, or we can add 1 number of times to construct strings of length I. And so that recurrence relation is going to be DP at I is equal to DP at I minus 0 plus DP at I minus 1. I minus 0 and I minus 1 are basically just valid indices, right? And the final count is simply basically to get the total count, we simply have to just sum up all the values of DP at I, basically where I is in between low and high, because again, that's what a good string is defined to be, strings that we can construct from the two operations we have to decide off of that are having a length in between low and high inclusive. So basically I has to be less than or equal to I has to be less than or equal to high, but I also has to be greater than or equal to low. Right? So with that kind of high-level rundown of the solution out of the way, let's go ahead and dive straight into the code here. So first of all, the problem actually asks us to mod our answer, our result, by 10 to the 9th power plus 7. So I'm just going to quickly define that variable so I can actually return my answer modded by that real quick at the end of the solution. So I'm just going to set mod to be equal to 10 to the 9th power plus 7. Again, this really large prime number that is, I think, used for encryption. I may be wrong. But anyways, this is really just because the problem actually asks us to modulo the value to actually handle large numbers and prevent integer overflow. But now let's actually get into the dynamic programming part of this solution. So first of all, we actually want to initialize or create that DP array to start building off indices I in it, right? So I'm just going to initialize our DP extra array. And it's going to be filled with zeros, and its dimensions is simply going to be 0 times high minus 1. Because think about it, we never have to actually exceed high minus 1, because we don't care about strings that are having a length greater than or equal to high, or rather just greater than or high. That doesn't really matter for us, right? And again, it's going to have size high plus 1, and all of them, or rather all the elements, are going to be equal to 0. Right? And what this really does is it's going to store the number of ways to construct good strings, or rather just strings in general, of each length from 0 up until high. And we also have to have now our base case. What did we say our base case was? Well, the base case, like we talked about before, is because there's going to be basically one way to build a string of length 0. Right? That's basically just by sitting down and doing nothing. And so DP at 0, basically a length of 0, is going to have exactly one different way. So I'm just going to quickly update DP at 0 to be a 1. And the reason why, again, is because there's only one way to construct a string of length 0. Now let's actually start processing all the possible lengths from 1 to high, and then build our DP array in that corresponding range to get all the answers between low and high for every index I. So for I in the range of 1 up until high, but in Python, the second parameter is going to be exclusive for the for loops here. So I'm going to have to do high plus 1 to go up until high, right, to actually iterate over all the possible lengths from I to high to again calculate the number of ways to construct strings of each length. So the first conditional we have to check if this is a valid indice is if I minus 0, if it's actually greater than or equal to 0. So if it's actually in bounds, then we know we can set dp at I and increment its value dp at I minus 0. Right? And what this really is doing is that we're simply just basically checking first on line 8, is it actually possible to add 0 number of times to construct a length, or rather to construct a string of length I? And if I minus 0 is actually a valid index, so if it's actually greater than or equal to 0, if it's non-negative, well then we can add dp at I minus 0 to dp at I, because basically, I minus 0 is actually a valid index. We're checking if it's possible to add 0 zeros to actually construct a string of length I. And then the second conditional we have is basically the same thing, but for 1, the 1 parameter. So if the current index minus 1, if that's still in bounds, so greater than or equal to 0, if it's actually a valid index, well then we want to increment dp at that index I by dp at I minus 1. That's the other decision we can possibly have to add 1 ones to this current index, right? So basically, again, very similar approach here. We're just basically checking if it's possible to add 1 ones to construct a string of length I, and if I minus 0 is valid, well then we want to add its result or value to dp at index I, the current index that we're processing, right? And once we do that, well then we actually want to get our mod part of this solution. So we want to set dp at I and simply mod it by the mod. So mod equals mod. Right? Because again, after each update, we have to actually take the modulus of 10 to the 9th power plus 7 to make sure that our numbers at this index I don't actually grow too large. Okay, that's great. Now let's actually initialize a variable total count. And I'll explain this in a quick second here. What total count is really going to do is it's simply going to store, or rather, it's going to have the sum of all the valid counts of lengths in between the range low and high, because the problem says that a good string has to have a length between low and high, and this is going to have the number of different ways or indices that have a length or value in our DP array between low and high, because that's exactly what the problem wants. We want to store the sum of all the valid counts at every index I in our DP array within that range low to high. So now let's actually get that and then increment our total count accordingly. So for I in the range of low to high, because that's the range we're actually looking for to check if we actually have valid lengths, and in this case it's going to be high plus 1 again because it's high plus 1 exclusive for loops in Python. So really this is just iterating over low to high. And in this range, we want to increment to our total count. So total count plus equals dp at index I, and then mod its corresponding result, total count. So mod equals the mod variable. Because again, we don't want it to actually get too large. And so at each step, we're going to mod it by 10 to the 9th power plus 7. Right? And what we're really doing here is simply just looping through all the elements from that range low to high and adding up the values of dp at index I, and effectively once this for loop is done executing in the range of low to high, we simply want to return whatever our total count actually is, right? Because that's going to be the result of our problem, all the strings of lengths that are in between the range low to high once we actually added their value correspondingly to the total count. So unless I made any syntax errors here, this should be accepted and this should be a valid solution. And as you can see, this is just about as efficient as you can get. So for a quick high-level rundown of how this code actually works as a whole, effectively, we're just using this dynamic programming solution to calculate the number of ways to construct strings of each length from 0 to high with our two operations. Either we can follow the constraints of appending 0 zeros or 1 ones at a time at each operation. And basically, by summing up all the different counts for lengths within the range of low to high and adding it to the total count for dp at index I in that range, we're going to get our desired result, which is stored in total count, which is what we actually return as our result. So for the time complexity, this outer loop here is actually going to run from 1 to high, right? Because that's literally what the for loop's parameters are. And the inner operations, which is simply just checking and updating our DP array, are all going to be big O of 1 or constant time operations. And so the overall simplified time complexity is going to be big O of high. And the space complexity, since we actually use that DP array of size high plus 1, it's going to have dimensions or size high plus 1. The memory complexity is also going to have a complexity of big O of high. You may be asking, why is it not big O of high plus 1 if that's the dimension of our auxiliary memory DP? Well, the reason why is because coefficients or constants in memory and space complexity and time complexity, they don't matter. So simplifying this, we really just make it go from big O of high plus 1 to a simplified space or memory complexity of big O of high, which is a very, very efficient solution for these input constraints, which are 10 to the 5th power. So if you guys enjoyed this solution and learned something new, please consider liking this video and subscribing to my channel. And without further ado, I will see you guys in the next video. Bye-bye.